All right, we're going to take a look at the even numbered problems on your practice, and hopefully that will help you with the odd numbered problems. In question number 2, we're given the function y equals 2 root x. We want to go to our BFF and see what our parent function is, and our parent is y equals the square root of x. The only thing we've done to that graph is to put a 2 in front. It is multiplying. It is on the outside, so that makes it a vertical stretch. All of our y values are going to be larger. So we can do that with points, or we can do that with a table of values. Starting with a table of values, we'd go back to our parent function, our BFF, and here are a few good points on our parent function. In order to get to our transformed function, because this is a vertical transformation, we would simply multiply all of our y values by 2. 2 times 0 is 0, 1 times 2, 2 times 2, and 3 times 2. There are no horizontal changes, so those x values will stay exactly the same. And then you could go and plot those points that are in blue and see the final graph. Another way to do that is to look at your parent function points on your graph. So I'm plotting 0, 0, 1, 1, and 4, 2, and 9, 3 on my graph. Because this is a vertical stretch, that means that each of these points will be twice as far from the x-axis as they are right now. So the first point is on the x-axis. So when we transform our graph, should show here in blue, that point will not change. But this point that's at 1 will now be twice as far, so it's going to go up here to 2. This next point is 2 units away from the x-axis. Now it will be 4 units away. This last point is 3 units away, so now it will be 6 units away. And when we connect the dots, we can see our square root shape that has been vertically stretched. The domain here, if we are looking left and right at our x values, they do not go further left than 0, and that is a point on the graph, so we're going to use the bracket to note that it's included, and it extends all the way to the right to positive infinity. As we look for the range up and down, it does not extend past 0, but it does go up all the way to infinity. So that's a vertical stretch on our square root graph. Next, we'll move on to number 4. Number 4 is a rational function. Our parent is y equals 1 over x. For our transformations, we've added 4, and that is grouped together with the x just by virtue of being in the denominator. And that means it's lying. So we're actually going to go to the left by 4, and the minus 3 that is on the outside of the fraction tells us we're going to go down by 3. So when we consider the original graph, remember that we have asymptotes at x equals 0 and y equals 0. And those will change as our graph shifts around the coordinate plane. Now, if you're a point person, when we graph our rational function, there are only 2 points to keep track of, those ones that are in the corner, which are 1, 1, and negative 1, negative 1. Sorry, I'm going to put those as our original points in a different color in black here. Because we're going to the left 4, our new x coordinates would be by subtracting 4 from where we originally were. 1 minus 4 would give us negative 3. Negative 1 minus 4 would give us negative 5. For our y values, that's a vertical change. We're going down by 3, so we can find our new y coordinates by subtracting 3. 1 minus 3 would be negative 2, and negative 1 minus 3 is negative 4. So we have our two new corner points. When we draw our new graph, we have to remember that our asymptotes are going to change as well. So I'm going to draw those in first. You can see the parent asymptotes in yellow here. When we transform our graph, when we shift it to the left by 4, that's going to take our vertical asymptote, which has an equation of x equals 0, and shift it left by 4. So our new asymptote is over here at x equals negative 4. When we shift our graph up and down, the horizontal asymptote is going to change. So it's going to go from 0 to negative 3 because we're shifting the whole graph down by 3. So there's our new asymptote. And now we'll plug in our points. So we got our points by looking at our table of values. That's option 1. Option 2, here are our parent points, 1, 1, negative 1, negative 1. And our transformations are to go to the left 4 and down 3. So if I start with this point that's in the right corner, and I go to the left 4 and down 1, 2, 3, I'm right here in this corner. And if I take this point that's at negative 1, and drag it to the left by 4 and down 3, now we're in this corner, and then we just follow our asymptotes and do our best to draw a curve through that point following the asymptotes. So our final graph would be in blue with the orange asymptotes. When it comes to our domain, we have an arrow over here that extends all the way to the left, which is negative infinity. And then our graph comes in, and it avoids this value of negative 4. It picks up on the other side of negative 4 and continues to positive infinity. So an alternate version of that interval notation I just wrote is just to say x cannot equal negative 4. Our x's are everywhere except negative 4. The range would work out a similar way. There's an arrow pointing down to negative infinity. We come up and we skip the value of negative 3 and pick up on the other side and go to positive infinity, which is another way of saying y cannot be negative 3. So either option is just fine as you express domain and range of this rational function. We're going to move on to number 6 next. We see another square root, but we have multiple transformations here. So our parent function is y equals root x. So we should already be able to kind of visualize what that shape is on our mind. If we are thinking about our parent points, 0, 0, 1, 1, 4, 2, you can put 9, 3 in there if you want. And then we're going to look at our transformations. The 3 is multiplying on the outside. That makes it a vertical transformation. It's going to do exactly what it says it's going to do, and it's going to stretch those y values. It's a vertical stretch. The 2 is grouped with the x. Therefore, it's going to do the opposite of what it appears to do. We're going to shift our graph to the left by 2. So if you prefer to work with points in a table, we're going to have to do two things. The first thing we're going to do here with y values are multiply those by 3. They're going to be 3 times bigger. And again, we're working our transformations from left to right. When we multiply by 3, 0 times 3 is still 0. 1 times 3, 2 times 3, and 3 times 3, 0, 3, 6, 9. When we change our x values, we're going to the left by 2, so we're going to subtract 2 from each of these points. 0 minus 2 is negative 2, 1 minus 2, negative 1, 4 minus 2, and 9 minus 2 is 7. So that's option 1. You have 4 ordered pairs that you could plot and get a great picture of your graph. We could also do this visually. The first points I'm going to plot here are the parent function. We have not changed these yet. And there they are in black. And because we have a stretch and a shift, I'm going to do the stretch first in pink and then the shift in blue. So the vertical stretch says that each distance between the point and x, the x-axis, will be 3 times as large. This difference is 1, now it's 3. This difference is 2, now it's 6. This difference is 3, now it's 9. So there's our vertical stretch in pink. We still have to shift our graph to the left by 2. You'll notice that, sorry, I should put a pink point here as well. 0 times 3, it's already on the axis, so that distance does not increase. Now we're going to shift each of these points to the left by 2. So our point at the origin goes over here, 2 spaces to the left, 2 spaces to the left, 2 spaces to the left, 2 spaces to the left. And then in blue, we're going to commit to this one. It's our final version. And you'll notice this graph has all the same points that we just put on the table. Here's -2, 0, -1, 3, 2, 6, 7, 9. So it all works out in the end. Now when we go to domain, we're going to need this point where the graph ends, and that coordinate point is -2, 0. It's going to help us figure out our domain and range. So the domain is left and right, and our graph does not go any further to the left than -2. -2 is a point on the graph, so we'll use the hard bracket there, and then it extends all the way to the right to positive infinity. Our range is looking up and down. Our graph goes no lower than 0, and 0 is a point on the graph, so we'll use the hard bracket there, and we have an arrow pointing up to positive infinity. That's our square root function with a couple of transformations. On to number 8. Here is our absolute value graph, v for value. We know it's going to make that nice pretty v. So our parent function is y equals the absolute value of x. And we actually have 3 transformations. The negative in front takes all of our y values and makes them negative. It's going to make our v open down. Mathematically, we say that that is a reflection over x. And then we have a 2. That's a multiplier. It's on the outside. That's going to be a vertical stretch. And then we have +1. That's going to move our graph to the left by 1. It's grouped together with the x, so it is the opposite of what it appears to be. If we're working with points, here are some good ones to work with on your absolute value function: -2, 2, -1, 1, 0, 0, 1, 1, maybe 2, 2. Slide that one in there. And we're going to work our transformations in order from left to right. The first transformation is the reflection and the vertical stretch. We can do that all at once if we're working with points. What we're going to do to get our reflection and vertical stretch at the same time is to multiply our y values by -2. The negative does the reflection, and then the 2 does the vertical stretch. So 2 multiplied by -2 becomes -4. 1 times -2. 0 times -2, still 0. 1 times -2, and 2 times -2 again, there's -4. Our only horizontal change is to go left by 1. So we're going to take these x values and subtract 1 from them. -2 to -3. -1 minus 1 is -2. 0 minus 1, that goes to -1. 1 minus 1, there's 0. And 2 minus 1 gives me 1. So if you prefer to plot points, this table has 5 points that are on your completely transformed function. And those are going to correspond to what we're doing graphically now. So here on the graph in black, I'm putting the parent function. Just a few points, those first kind of 5 points that we see on our v. And before I shift it, I'm going to reflect it and stretch it in pink. When we reflect over the x-axis and multiply by 2, the point at the origin is not going to change. So that's still going to be at 0. And again, we're doing this in parts. I'm going to do the stretch and the reflection first. This point that's at +1 is going to come down here to -1 on the reflection, and then it's going to stretch to 2. This point here at +1 is going to come down to -1 and then stretch to -2. This point up here at 2 is going to reflect to -2 and then stretch to -4. And I'm sure you can see the pattern. This point at 2 will reflect to -2 and stretch to -4. Now to get our final graph, if we're working visually with our points instead of with a table, we need to shift each of these to the left by 1. So my final graph will be in blue, to the left by 1. And the blue graph is our final stretched and reflected and shifted absolute value function. Domain and range, I think this vertex, this reference point is going to be really important. And I can see that that is at -1, 0. So I'm going to go ahead and put that on my graph to help me with domain and range. Oh, well, domain is all real numbers. I have an arrow to the left, an arrow to the right. So pro tip of the day, if your parent function has a domain or range of all real numbers, that can't be changed no matter what we do to it with these transformations. But our range, a little bit different. We're looking up and down. I see an arrow going down to -infinity. And as we trace our graph coming up, it stops right here at the axis. It stops at 0. And that's a point on the graph, so we're going to include a hard bracket. So this is our reflected, stretched, and shifted absolute value graph. And you're welcome to work with points on the graph or with a table of values, whatever makes you most comfortable for graphing. Now we have one more even numbered problem, and then I'm going to ask you guys to do the odd numbers. Hopefully this will help you get those started. And our parent function in number 10 is that rational function with the asymptotes. And it looks a little funky. Our 1 turns into a 6. So you might rewrite this one, because it would be the same, as writing 6 times 1 over x. That 6 is really on the outside. So when the 6 is on the outside like that, we're going to recognize that our transformation is a vertical stretch. We're multiplying by 6. So let's list our x and y points that are on our parent function, the original. And remember with the rational, there are only 2 of them, 1, 1, -1, -1, those points in the corner. So we're also going to think about our asymptotes. 2 of them. I'm going to draw the parent asymptotes in yellow so we can change them if we need to. And let's label those. This guy is x equals 0. And this horizontal guy, y equals 0. All right, now we only have one thing happening. We only have a vertical stretch. That tells us we should multiply our y values by 6. 1 times 6 is 6. -1 times 6 is -6. And the y values don't change. It's still 1 and -1. So we multiplied y values by 6. Okay, so we have an asymptote whose equation is y equals 0. So we have to ask, is that going to change? Well, if we multiply 0 times 6, it is still 0. So our asymptotes are not moving. This is a y transformation. The asymptote with y is 0. Multiply it by 6, still 0. So we're going to plot our new points in the corner using the table of values, if that's your preference. We can also do this with points on our graph. So again, here are the black points on the parent function in black. And I look at the first point. I know we're stretching that vertically by 6, so the distance between this point and x, which is currently 1, needs to stretch to 6. 1, 2, 3, 4, 5, 6 needs to be 6 times bigger. So it's up here. And this point that's at -1 is 1 below the x-axis, so that needs to stretch to be 6 times bigger. So we're going to draw that down by 6, or to -6 rather. 1, 2, 3, 4, 5, 6. And in order to follow this curve now, we're going to have to kind of turn in earlier here to hit that point. And this is what our vertically stretched graph looks like for our rational function. Because the asymptotes didn't change, the domain and range are really the same as the original function. We're avoiding the same values. So for domain, depending on how you want to write that, you can write -infinity to 0 and then 0 to +infinity. It's option 1. You can also say x does not equal 0. Goes everywhere except for 0. Range, same thing. -infinity to 0 in set notation and 0 to +infinity, or y cannot equal 0. That gives you a couple of options for how to transform these graphs. You might practice with both, see which one makes you the most comfortable, whether it's points or doing some plotting in different colors and moving your points around the graph. So take the time to do those odd-numbered questions, and anything that you're stuck on, bring those questions back to class next time I see you. Good luck.